Hi there. Now, in this next part, we're given instead that the level of A is below the level of B. And what we've got to do is show that P does not reach B. So what you can see is I've already redrawn the diagram with A below B. Remember, we're told that the particle P is projected now from A at 5 meters per second. The distance AB is 2 meters. So if you'd like to have a go at this, show that P does not reach B, then I'll give you a moment just to pause the video. When you come back, you can check your work solution against mine. Okay, welcome back if you had a go. Now what I'm going to do here is I'm going to work out the distance that the particle P goes up the plane before it comes to instantaneous rest. And I'm hoping that that distance is going to turn out less than 2 meters. So I'm just going to say that the particle comes to instantaneous rest at some point up here. Okay, so we'll mark that in as 0 meters per second. And I'm not assuming that that distance is up to 2 meters. So there's going to be a change in speed. So there's going to be a deacceleration. I'll mark in though an acceleration arrow, A, okay, as A meters per second. I would expect A to be a negative value because it's slowing down. It slows down because it's going up the plane and it's also on a rough incline plane. Now to work out the distance it travels up the plane, I'm going to want to turn to one of the constant acceleration equations, often known as the Suvat equations. But I'm going to need to work out what A is first of all. And to get A, I'm going to need to mark on some forces on our particle P and apply Newton's law of motion. So let's go to putting on some forces now. Well, we've got the weight of the particle, P, okay. We know its mass is 0.4 kilograms, so the weight is going to be 0.4 G newtons. There's also going to be a normal contact force with the plane, so that's going to be R, okay, R newtons. Now there's friction involved. Remember, it's going up a rough plane, and friction always opposes motion. So that's now going to be in the downward sense, okay? And because it is actually moving, friction has reached its limiting value. It's equal to mu r, the coefficient of friction, times the normal contact force. We know that the coefficient of friction is 0.2, so this is going to be 0.2 R newtons, okay, for that frictional force. Now they're all the forces acting on our particle. And whenever I'm doing work on inclined planes, I always mark a dotted line in like that. And this angle here between the weight and the dotted line here is always the same as the angle of the plane. Okay, so that is going to be 45 degrees. So with that, I can now start to work out what the acceleration is by applying Newton's second law of motion. Force equals mass times acceleration. But I'm going to need to get R when I look at resolving up the plane. So to get R, I'm going to need to resolve perpendicular to the plane. And this result for R is exactly the same value that we had in the very first part of the question. So if you're unsure how I got that, okay, just go back to the very first part. I resolved perpendicularly to the plane and I found out that R would equal 2.7718 and so on. And that was measured in newtons. So now all I've got to do is to resolve in the direction of motion up the plane, okay? So I'm taking up the plane as positive, so we'll resolve up the plane. Always take positive in the direction of motion. So applying our force equals mass times acceleration, looking at the forces acting down or up the plane, we've got all of this frictional force acting down the plane in the opposite sense to what I've got here. So it's going to be negative, and it'll be 0.2 multiplied by r being 2.7718 and so on, okay? As for r, that's not going to enter this equation because it's perpendicular to the direction I'm resolving in. Now as for the weight, this force here is inclined at an angle to the direction we're resolving in. And so looking at the components of this, which we looked at in the very first part of the question, we've got this component down the plane of the weight that we're interested in, which was 0.4 g sine 45 degrees. And that will be in the negative sense. So if we take that into account, we've got minus 0.4 g sine 45 degrees. Okay? And this will be our resultant force acting on the particle down the plane. So let's take those components away, because normally I don't put them on, I just imagine them. Then we've got this resultant force equals the mass times the acceleration. Well, the mass is 0.4 kilograms, so we've got 0.4, and we need to multiply that with a, the acceleration. Now if you work out the left hand side here, taking g to be 9.8, what you therefore have is minus 3.326 and so on equals 0.4a. And if you now divide both sides by 0.4, you end up with a equaling minus 8.3155 and so on meters per second. So a's come out as a negative value, just as we would expect, so it's slowing down. So all we need to do now is just apply one of our constant acceleration formulas, the Suvat based equations. So if we write down our variables here, s, u, v, a and t, we need to take a positive sense, so I'm going to take positive as being up the plane. So s is for displacement, that's what we're trying to find out, so we'll put a question mark there. U is the initial velocity, which was 5, okay, meters per second. V, it comes to instantaneous rest at some point, so that's going to be 0. The acceleration we've just found out is minus 8.3155 and so on. As for t, we're not interested in that, so we can just ignore that. So what equation connects these variables together? Well, it's got to be v squared equals u squared plus 2as. And if I rearrange this for s by subtracting u squared from both sides, we'll get v squared minus u squared equals 2as. And then if I divide both sides by 2a, I end up with s equaling v squared minus u squared, all divided by 2a. And using this, I therefore have that s is equal to v squared, so that's going to be 0 squared or 0, minus u squared, u is 5, so we've got 5 squared there. And this is all divided then by 2a, so that's going to be 2 multiplied by negative 8.3155 and so on. And if you work this out, remember you've got a negative here divided by a negative here, it's going to give you a positive value for s, and it turns out to be 1.503 and so on. And this turns out to be less than the distance AB of 2 meters, so it's less than 2 meters. So our conclusion is that P, the particle P, does not reach B. Okay, just put that conclusion in. So, hope you've been able to see how to do that, and well done if you were able to get that one right.